calculate moment generating functions for continuous random variables. So just in retrospect, a moment generating function is a function that generates moments. So if you remember, you end up with this sum of moments, and why you would want a moment generating function is, for instance, in some cases, it is difficult to find the moments using the techniques that we studied in class. So if you can find the moment generating function, then you can easily find the moments, because there really are times, like I said, when it's not that easy to do it from the definition. So just for starters, we just want to start off with the definition of a moment. This you already know, so I won't linger on it, but I just wanted to show you that the definition of a moment is the same whether the random variable is discrete or continuous. So in this case, the kth moment about the origin is just the expected value of y to the power of k. And then the kth moment about the mean is this, which is exactly what you had in the discrete case. So when you hear the words moment of any type, any of these types, it's the same thing that I'm asking you for. Now, if we come back to these formulas here, this is the expected value of a function of the random variable. This is the case for discrete on the left, and this is the case for continuous, and we established this is the definition in class. So now I want to look at this case of hx. So it's a special example. If I take hx to be e to the power of tx, then in the discrete case, that's just the expected value of e to the tx. So you know that whatever's in there as a function of x just ends up being in that position. And what you end up with is this, which is just the definition of a moment generating function for a discrete random variable. Now, similarly, this is what you have for the moment generating function of a continuous random variable. Instead of a summation, you have an integral from minus infinity to infinity. And in place of the hx, from here, you have e to the tx. And instead of using a probability mass function, you're going to use a probability density function. Now, on page 175, you will find the definition. This is in your textbook, exactly what I just showed you. And here they add on this extra little bit. And they say that the moment generating function is defined for values of t in a specific interval. So there's a restriction on that interval. That interval needs to include the value of 0. Or in other words, the valid region for t needs to have both positive and negative values of t. The other property that also holds for the continuous is this one. If you take t equal to 0, the moment generating function must be equal to 1. So this is very easy to prove, so we'll do it very quickly here. So you start off with mx0, which is just substituting 0 into the moment generating function, and you end up with this in place of t. So according to the definition, this is what the moment generating function looks like. And e to the power of 0x is equal to 1. Therefore, you're just left with this integral over the PDF. But remember, for a PDF to be valid, which is the assumption in this case, the area under the entire PDF must be equal to 1. Another property of moment generating functions is that even in the continuous case, moment generating functions are unique. No two different distributions are going to have the same MGF. If they have the same MGF, it's the same distribution. So now we're going to have a look at an example. Consider the continuous random variable x with that PDF, defined for x values greater than 0 and 0 otherwise. In this example, we need to find the moment generating function. Okay, so in order to find the moment generating function, we're going to start off with the definition. So the definition of a moment generating function is as follows. Okay. Now, obviously, this is just a special hx function, so this expected value for continuous random variable is the integral from minus infinity to infinity of e to the tx fx dx. All right, so now we're just going to substitute fx in there, but remember that domain of excess fx runs from x is equal to 0 up to infinity. So I'm not going to bother with the other values where this function is equal to 0 because the integral is just going to be 0. So the next line, instead of minus infinity, I'm going to put 0 and x goes all the way up to infinity. And then it's still going to be e to the tx times e to the minus x dx. Okay, so now if I just focus on those powers, they have the same base, so you can just add the powers. I'm just going to do it on the side here. So tx minus x is just equal to x times t minus 1. Okay, let me move that down. Sorry about that. Okay, so since we've just agreed that's the case there, I'm just going to substitute it in the power. So the integral is from 0 to infinity, e to the power of x t minus 1 dx. So it's exactly what I have there. But we know that now the integral of e to the power of a function of x dx is just e to the power of fx, so exactly that thing, but divided by the derivative of the power. Okay, so what that means for us in that case is we're going to copy exactly what's there. Oh, dropping the integral now, becomes t minus 1. And then we divide by the derivative of the power. So the derivative of that is just t minus 1. So now we need to substitute the upper and lower limits. So it's from 0 to infinity. Okay, I'm going to take out this constant here. So the 1 over t minus 1. So that we just left with the part that depend on x. So it's t minus 1. And remember, you always subtract the upper limit from the lower limit. Okay, so to write it correctly mathematically, the upper limit is expressed as follows: e to the power of x t minus 1. Okay, because it's not a specific value, so you can't just put it in. So we're writing it this so that it's correct mathematically. You say the limit as x approaches infinity minus, here we have a specific value, so it's e to the power of 0 t minus 1. Okay, so that's that square bit there. So now I want to have a look at this bit here where you have the limit. So I want you to notice something. Okay, if, okay, t minus 1 is greater than 0, then we notice that the limit as x approaches infinity of e to the power of minus x t minus 1 just goes towards infinity. I hope you agree with that. So what you have is this positive infinity times this positive value. So e to the power of a huge positive value, it just goes towards infinity. On the other hand, if t minus 1 is negative, then that same limit, e to the power of x t minus 1, goes towards 0. So imagine here you have a huge positive number, and here it's times a negative number. So remember, when you have a negative number in the numerator, you take the reciprocal. So it ends up being 1 divided by e to the power of this thing. And obviously, if the denominator gets larger and larger, then that limit is going to go to 0. So this is just a side note. So now, in order for this thing to be defined, obviously, we can't consider values that are t minus 1 values that are infinity, because this thing is not going to be defined. It's going to go to infinity if you put infinity there. So we're going to restrict this, the domain of t, so that you get a specific defined moment generating function. So in this case, if we restrict t minus 1 to be less than 0, we know that this limit's equal to 0. So in the next line, this is an important part, you're going to say, I'm just going to keep that. We're going to substitute 0 in there. And obviously, e to the power of 0 is just 1. And then you're just going to add here for t minus 1 less than 0. And you can actually rewrite this thing. So if you put the 1 on the other side, so this holds for t values that are less than 1. So you end up with minus 1 times 1 over t minus 1. So if you multiply by minus 1, you actually get 1 over 1 minus t. And this is important. Always remember to say this restriction, this t less than 1, because typically a mark is awarded for this extra bit here. So if you remember, for the definition of the moment generating function, we said that this function needs to be defined for t values that include 0 in that interval. So if you look, t is less than 1 and 0 is in that interval. In the definition, it also said that another way of expressing this is that t contains both negative and positive values. So that region contains both positive and negative values. So you can just see that here. You have positive values between 0 and 1 and the negative values below 0. So that satisfies that property. Another thing, now let's say you're on this part. You get to the end. You're not really sure what you should have done there. Suppose you did get here. Another way to verify whether this is correct, the moment generating function should always be positive. I'm just going to make a note there. So the moment generating function, sorry about that, should always be positive. So here, notice that if you take t values that are greater than 1, then you end up subtracting a big negative number, so this becomes negative. So when we restrict t to be strictly less than 1, you can immediately see here that this is always going to be positive, so that makes this MGF always positive, and that's one of the properties. Let's have a look at another example. This is example 4.15 in the textbook. It says, at a store, the checkout time x in minutes follows that PDF for x values greater than or equal to 0 and 0 otherwise. And we have been asked to find the moment generating function for this PDF. So we start off with the definition of the PDF as follows. So it's just a direct application of that. And then in the next stage, we're going to substitute fx. So everything else remains the same, except the limits. I'll get to that just now. So in place of fx, you put t 2e to the minus 2x, just directly copied from there. But this function is not defined, well, it's equal to 0 for all the values less than 0. So we can just focus on 0 to infinity. In the next step, they combine the powers. So you take the 2 to the outside there, and then if you factorize tx minus 2x, you can get this. It doesn't necessarily have to be that way, but this is what they've chosen. So after you've done the integration, this is what you end up with, and all that you're left with is to substitute infinity and 0, and then when you solve that, this is what you get for values of t less than 2. I just want to show you quickly, just expand on this part so you really understand. Now I'm just going to start from this step here. By this stage, you would have done the integration already, and all that's left is to substitute the upper and lower limit. So this is the next step that I have. I've taken out this term here because it doesn't depend on x. So it won't be affected by our substitution. It's merely a multiple on this exponent. So we're going to focus on this part where we substitute 0 and infinity. This part represents where you substitute infinity in there. This part represents where you substitute 0 in the same function. Okay, so remember you always find the difference, upper limit minus lower limit. Okay, so this is one of those examples where you're faced with that same dilemma where this thing is going to go to infinity for some values of t, and therefore the whole moment generating function will not be defined. But for some values of t, this thing is going to go to 0, and we will be able to find a closed form function for the moment generating function. So this is the basis of how you find that bound for t. So you're supposed to know this already. E to the power of infinity goes to infinity because it just goes bigger and bigger and bigger. But as x goes towards minus infinity, e goes towards 0. In order for this thing to go towards 0, this power has to go towards minus infinity. So obviously this part where the x goes towards positive infinity from there, that means this part has to be restricted to be negative so that the whole thing goes to minus infinity in the numerator. So that means this part needs to be less than 0. Okay, so you can rewrite that top part there, we want it to be less than 0. And you can rearrange that. So if you multiply both sides by minus 1, you get 2 minus t greater than 0. If you add t on both sides, you end up with 2 greater than t. So in order for this thing to go to 0, t needs to be less than 2. So now we can go to the next line, just a continuation. You have minus 2, 2 minus t. And we said this thing is going to go to 0 under that condition. And this thing, e to the power of 0, is just going to be 1 for t less than 2. Now you multiply both sides by minus 1, and you end up with 2 times 2 minus t for t less than 2. So you can see once again that the values of t that you have selected actually force the moment generating function to be positive for all values of t in that region there. So that's just another way of checking whether you have the correct region for t. Not every moment generating function is going to require that trick with infinity where you need to restrict t to be on a certain interval. Some moment generating functions actually are valid for t values that go from minus infinity to infinity. And I want to look at an example where you don't have to do that trick. So it's a little bit on the simpler side. So in this case, we want to find the moment generating function of this y. A and b are just constants such that a is less than b. So this is how you would proceed. Naturally, you start off by applying the definition. So this is directly that. And now if you substitute fy, then you literally end up just copying that function. This function is a constant, so you're allowed to just take it out. That's from this property here. So inside, you're just left with the integral from a to b of e to the power of yt dy. So notice here, we no longer have minus infinity to infinity because this PDF is only valid between A and B, or rather, it only has area between A and B. So we can ignore the region where it's 0 because the integral will definitely be 0. So this is where we are now. If you take the integral of e to the yt, so remember, this is what we're applying. So you're taking e to the yt and then dividing by the derivative of yt. The derivative of yt is t. So that's where this t comes from, and that remains there. Now all you need to do is substitute the upper and the lower limits, and this is what you end up with. E to the power of bt minus e to the power of at times this thing. Now this moment generating function, it does have a small restriction. T cannot be equal to 0. Obviously, if you put t equal to 0, this thing is going to go to infinity. You can't divide by 0. But for t equal to 0, the moment generating function is equal to 1, because this has to be a valid moment generating function. Remember that property. When t is equal to 0, a valid moment generating function will be equal to 0. Now this distribution I've just given you is actually a special distribution. In the way that you had special discrete distributions like the negative binomial and the binomial distribution, we also have special continuous distributions. This one is called the uniform distribution. So if y has this PDF, then you say y follows a uniform distribution with parameters a and b. So this y is fully defined by knowing a and b, the upper and lower limit of the interval. Shorthand, this is what it looks like. This is how you'd say that y has a uniform distribution with these parameters. And we just found that this is the moment generating function. And as I told you earlier that moment generating functions are unique, this actually applies to the PDFs and the CDFs. So if I give you a function that looks something like this, then it has to be uniform. It can't be anything else. If you get an MGF that looks like this, then it has to be a uniform distribution. A and B might be different, but if it can be expressed in this form, it must be a uniform distribution. I want to look at some examples just to demonstrate what I mean by that. Suppose we have a random variable w defined as follows. Fw is equal to 1 over 10 for values of w between 5 and 15 and 0 otherwise. So now if I asked you to tell me what is the distribution of w and the relevant parameters, what you do is you go to your list of different distributions and then you'll just compare what PDF does this look like. Okay, so I'm going to start off. The easiest thing would be to compare here. Okay, because the difference of any values, b minus a, it's easier. So many different values, I can have a difference of 10. So the starting point is going to be here on the bounds. So if we literally just compare, we have bounds 5 for A, 15 for B. So, okay, so it might be a uniform distribution with parameter 5, 15. But now we just need to verify that this is equivalent to B minus A. So we said B is 15, A is 5, the difference is 10. So therefore, you can now conclude immediately, since it holds, that W has a uniform distribution with parameters 5 and 15. Let's do one more example. Suppose I give you this moment generating function of a random variable v. Now, this does not immediately look like this moment generating function. So sometimes you will have to manipulate this to make it look like a moment generating function that you recognize. So for now, we only know the uniform, but there are different moment generating functions for different distributions. So it will be a little bit more complicated when you know more, but they look so different, it's not going to be that much more complicated. So we're going to manipulate this a little bit. Here we know that e to the t from there is e to the power of 1t, just to make it explicit what the coefficient of t is. And we know that 1 is equal to e to the power of 0. And we can throw in a t there because it's still going to be 1. So now we've got the numerator in that looking like this numerator. So b is 1, a is 0. So we just need to verify as well that it holds for the denominator. And fortunately, it does. So the difference between b and a, which is 1 and 0, is just 1. So you can see if you look at the form of that moment generating function and the form of this one, they look exactly the same, except that you now have values for a and b. A is 0 and b is 1. If, for instance, like let's say the denominator hadn't worked out to be 1, then you wouldn't have been able to conclude that this is true. It has to look like that one. So if this one hadn't worked, then you would have tried another different distribution. So remember I told you that a moment generating function pretty much generates moments. So to express that explicitly, this is what you have for a continuous random variable. So from the definition, this is exactly what you're going to get. And then let's go step by step. That e to the ty can be expanded as follows. Okay, so this is just a result. You don't have to prove it. It's just true that e to the ty can be expressed as this infinite summation. So now when you have a summation, you're allowed to put the integral inside around each of the terms. And then don't forget outside, we also have this fy. So we also need to multiply each term inside by fy. So in the next step, you end up with 1 times fy surrounded by the integral. This part you have ty times fy surrounded by the integral, and you can keep doing that. Now the term t obviously doesn't depend on x, that whatever t is, it's a number t, so you can take it out. Here 2 squared over 2 factorial also doesn't depend on x, so you can take it out. So now if you look inside, that's just the definition of the expected value of y. That is the definition of the expected value of y squared. That's the expected value of y cubed. So now if you use a shorthand notation, so that's just the first moment, that's the second moment, and that's the kth moment. So what you see is you end up with this summation of moments. So it literally generates moments. That's why it's called a moment generating function. We're now going to have a look at the properties of the moment generating function for a continuous random variable. So in the discrete case, remember that all of these properties held. So the expected value of x to the power of r is equal to the rth derivative of the moment generating function with 0 substituted in place of t. And similarly, the way you calculate the mean and the variance using that rx function, it actually holds for the continuous in both cases. So you're going to follow the same procedure in what you did for the discrete for a continuous random variable. Another property that also holds for a continuous random variable is this one. So if you have the moment generating function of x and you get a linear combination like this, then the moment generating function of that linear combination is just this term over here. Now let's have a look at an example. So this is the example we did earlier. We found that the moment generating function was 1 divided by 1 minus t for t values less than 1. So now in part B, we're asked to find the mean and the variance of x. So in order to find the mean, remember it's just that first derivative of the moment generating function with 0 in it. So according to the chain rule, if you find the derivative of this thing, you end up with 1 minus t to the power of minus 2. In order to get the expected value, we need to just plug in 0 into this function. So therefore, our answer becomes 1. Now, in order to find the variance, remember this is a shortcut formula for the variance, we're going to need the expected value of x squared. We already have this one. So in order to get this one, it's just the second derivative of the moment generating function with 0 substituted in place of t. So to find that second derivative, we're going to use the chain rule on this line again. So we do another derivative there, and you end up with this function here. Now, substituting 0 only gives you the expected value of x squared, and that's going to be 2. So in order to get the variance, we need to take our answer from there and our answer here, and ultimately you end up with 2 minus 1 equal to 1. So that's exactly how you would work out this example.
Lastly, please note that the following section is excluded. So about halfway down on page 174, you'll see a small section titled Approximating the Mean Value and Standard Deviation. So that little section is excluded. You don't need to look at it. You completely skip it. It ends about halfway on page 174. Okay, so that brings us to the end of section 4.2.